Welcome back to the series of lectures on high-performance scientific computing. Over the past few lectures, we have been discussing how to program distributed memory machines using the message passing interface paradigm. We will continue on this journey. Today, we will look at a few more MPI-specific functions, especially which aid in the communication. We had talked about functions like MPI broadcast, MPI scatter gather, MPI all gather, so on and so forth. So today we will look at a few examples on how this is used practically. We had discussed the collective data movement. We had given this picture where there are 4 processes P0 to P3, and in the first case we had an idea of taking the variable A, which is resident only in P0, and we wanted to communicate it to all the other processes. Now, if we did not have the broadcast functionality, the only way to transmit this data would have been to have 4 MPI sends and 4 MPI receives. Similarly, if you wanted to scatter a vector, for example, if the process 0 had a vector which had 4 elements A, B, C and D, and you wanted to partition this vector in such a manner that you wanted to send B to the process P1, C to process P2 and D to process P3, we then needed to do it correspondingly with 4 MPI sends and 4 MPI receives. But now MPI gives us a scatter gather functionality which allows us to scatter this array amongst these 4 processes, and then also in turn, if you want to bring the data back and assemble it into the same single array, we can have a gather function. Now, one of the questions would be, where is such functionality useful? So we will now see a mathematical example of the usefulness of such functionality, and then we will see a simple implementation of that math functionality in the code. One of the mathematical problems that can be handled by this functionality is the dot product. Let us assume that there are 2 vectors A and B, both of size n. The dot product now is defined as the sum of all the individual products of AI, BI from I going from 0 to n minus 1. And when you take the summation of that value is a dot product. Now, you can do this serially, but instead of computing the dot product on a single processor, now we can distribute the computation across multiple processors. To give you an analogy, let us now assume that you had 2 bags of integers instead of a single bag of integers like we had argued in the past. And we now want to compute the pairwise summation of each and every integer which is there in each of these bags. The way we can do it parallelly is that we take the bag of integers and distribute the first 1000 to the first person, second 1000 to the second person, so on and so forth, until all the 10,000 integers which we had assumed are there in the bag are evenly distributed among 10 people. Similarly, we take the second bag which also has 10,000 integers and evenly distribute the 1000 integers among the set 10 people. Now, each person will compute the local product first, local pairwise product, and then the local sum. Finally, you need to do a global sum to get the correct dot product. So how does the MPI scatter gather approach work? The MPI scatter function will take the root process which has all the entire knowledge of A and B, and it distributes parts of the vectors equally to all processes. Then each process will then compute a partial dot product using its individual data or its assigned chunk. Then we have to gather the data. So we can use either MPI gather or MPI reduce to collect all the partial sum so that you can compute the final product. We can see the implementation in code now. So to make matters simple and illustrate it easily, I have just said that the size of the vector is to be 8, i.e. both the vectors A and B have only 8 elements each. Now, because we are defining it in such a way and we are hard coding it, we must always have this sum which is divisible by the total number of processors which are available. Let us see what happens next. So we have the integers rank and size. Now we have this full vectors A and n, A of n and B of n, which is only used in the root process or the master process. Every individual process will then have its own local copy or its own local storage. We are now making the assumption over here that there are going to be 4 processes, and hence we are dividing n by 4. We have hard coded this, but we can always come up with an algorithm to make this more generic. This has been hard coded in for it to run in 4 processes to make the idea of gather and scatter simple. We then have to have 2 integers, one is the local sum and the other one the global sum. Here we are now initializing the MPI environment. We are finding out what is the size, rank, and we are proceeding over here. The total number of elements per processor is n divided by the size being the total number of processors we are giving in at the argument. Remember that we are supposed to select it as 4 because we have sort of hard coded the problem to be 4 over here. Now, what are we saying? The first thing is that we need to initialize the vectors in the root process with some value. Obviously, only the root process needs to have the values at this point of time, otherwise there will be no meaning of a scatter and gather. So if the rank is equal to 0, we have identified process 0 to be the master process. We are going and putting in values or initializing the values for the vectors A and B. We are setting AI to be I plus 1 over here. And so in the end, what you'll have is that A will be a vector which is 1, 2, 3, so on and so forth till 8. And B is nothing but twice A. So B is going to be 2, 4, 6, 8, so on and so forth till 16. And then we have to compute the dot product between A and B. The first thing that we have got to do is scatter both the vectors. So let us see how this is being done. So we are going to scatter the vector A, which is available globally, or rather only with process 0, but the whole vector is available there. We are going to say that we are going to scatter the total number of elements per processor. So now if you go back, in this case, we have n is equal to 8, and we are going to say that we are going to have 4 processors. So n divided by 4 should be 2. So that means we are going to scatter 2 elements per processor. We need to give it the data type, what type of data we are transmitting. We are saying that we are going to send an integer data type. We are going to send it to which destination array, and that's going to be the local A and local B. And remember, local A and local B have been initialized to a size of n by 4, which is basically 2 in this case. Now, since this is where the hard coding actually comes in, we can change these numbers to change the behavior of the program. Obviously, if you want to take this during runtime and not pre-allocate them, you will need to use some sort of dynamic memory allocation, examples of which we can see in more complex codes. So we are now going to say that we are going to scatter the data into local A and local B, and again we are going to transmit elements per processor, which is 2. The data type is again int, and more importantly the source. Where is the data coming from? So when you do the scatter function, so all the sends, the implicit sends will take place from process 0, and it will be sent to each and every other process. So what do I mean by that? Remember, I told you we could achieve the MPI scatter functionality by just using sends and receives. In fact, underneath, essentially, it is unrolling and doing sends and receives. So what this MPI scatter is saying that the process 0, which is the source, is going to do all the sends, but it's going to do partial sends in the sense that it's going to take the main array A, take parts of it. What is that parts? What is that length? That is elements per proc. And it's going to send that to all the other ranks. So for example, 0 will send to 1, 0 will send to 2, and 0 will send to 3 in this case because we have 4 ranks. So it breaks down the MPI scatter into 3, or rather, if there are n processes, n minus 1 pairs of sends and receives, where the sends are being done from process 0 and the receives are being done from every other process apart from process 0, that is 1 to n minus 1. So we have now two MPI scatters which will basically take the two vectors A and B, split it up into even parts and send each of those parts to different processes. And the first part obviously will be retained by process 0 because that's going to do some computation as well. Then once this scatter has been done, that means all the data has been transmitted and all the process each of them have their local data. Now you can compute the local dot product or the local sum, which is basically taking the individual product of each of the elements, local AI into local BI, and then totaling it into a local sum. Once this is done, you have to now reduce this local sum because each of the processes have computed only their local sum. You have to reduce it into a global sum, and that each of the partial results are now sent back to the root using the MPI reduce function. In the MPI reduce function, what's happening is that the local sum is now being added into this global sum. So if this is also breaking the MPI reduce into 3 parallel MPI sends and receives, but in this case the data is going from process 1 to 0, 2 to 0 and 3 to 0 because the destination for the reduction is rank 0, which is given over here. But there's an additional thing that this function does. That does is the summation. So for example, in the scatter, all that was done was copy different parts of the array into local arrays. In this MPI reduction function, there is a mathematical operation also that is being done. So first of all, this is a sort of a blocking function in the sense that each MPI rank other than 0 is going to send some information to rank 0. They are all going to be stored at one variable called global sum, but the way it is going to be stored is that as each individual variable comes in, they need to be sort of added into that memory location. So process 0 is going to wait. It's going to get the data from some other process other than rank 0. The order does not matter over here. So for example, process 2 might send its value first. Then process 0 will store it in global sum. And until the store is complete, it's not going to receive anything else into that particular memory location. Now process 1, for example, sends out its local sum. Process 0 at that point is going to take the value which is already there at global sum and add the value which is coming in from process 1 over there. Similarly, when process 3 eventually sends the last bit of information, whatever is the partial sum over there is now going to be added again to global sum, and finally the process is complete. So this is the reduction operation. Once this is done, you're basically complete and you have computed the dot product, and we need to print the dot product only once. So we will say, if you're rank 0, please go and print out the dot product, and then finally we finalize, close out all the MPI processes and get out of the program. Now let us see how to compile this program and run it. So I will say MPI CC dot product, put it to the output file dot product. Now immediately you see there's an error which has been thrown during the compilation process, and the compilation says that in line 20 and in line 31 that you are using declarations within the for loop. Now, if you want to use this sort of declaration where you have the integer declaration of the index is inside the for loop, or rather in the for specification, this is a C99 or a standard which has to be followed. Now, some compilers will ask you to pass a certain flag to use this sort of language. Remember, finally, all these codes and compilers are semantics which you have agreed upon. So the compiler needs to understand what language you're speaking to it, and in this case we're saying we're going to stick to the C99 standard, and hence we need to pass that information to the compiler. So now I will recompile this code by giving it the correct flag MPI CC minus std is equal to C99 dot product dot C as O and dot product. So in this case, compilation will be successful. The other option, if you didn't want to pass this flag, was to do the declaration of the integer in I outside this for loop and then say I is equal to 0. That's the second option you have. Anyway, now we have compiled the dot product. Let us now run this code. And we had initially hardwired it to run with 4 processors. So we'll say MPI run minus NP 4 and execute the dot product. And you'll see it has now computed 408. Now let us see what happens if I use a number of processors other than 4. You will see that if I use say 6 processors, I actually get an incorrect answer. This is because I had hard coded the number of processors to be 4. Now let us go back to the code and just get an idea of how we would actually complicate the problem by having any number of processors. We won't go through the full implementation, but I'll just give you hints and leave it at that so that you can implement it when you would like. So first of all, you would typically take the problem size as an input from the user. Second thing, once you do that, you will have to initialize both the arrays dynamically, in the sense that I will not know the problem size a priori. So I will have to figure out what the length of A and B is. So I have to allocate using the process called malloc and dynamically allocate arrays A and B. Similarly, I'll have to then figure out if the process is perfectly divisible amongst the number of processes I have initialized. This is again an runtime variable. If that's not the case, then I'll have to again allocate new local arrays which sort of use the modulus function and ensures that you allocate adequate memory at the local spaces. Please give this a try and figure out how you can change this program to dynamically take the input of the size of the vector and also dynamically take the input of the number of ranks that we are initializing. It would be an interesting exercise. Now let us just go back and review what we had done with the mathematical dot product. So here is the explanation. We had started an initialization, the root process with rank 0. It initializes the vectors A. The vector A is initialized as 1, 2, 3, 4, so on and so forth till 8. The vector B is initialized as 2, 4, 6, so on and so forth till 16. We took this vector, which is 8 long, and we scattered it amongst 4 processes. We gave the first process, process 0, 1 and 2, process 2, 3 and 4, process 3, 5 and 6, and process 3, 7 and 8 from the initial vector A. And similarly, we split the vector B. Each MPI process then computed the partial dot product. So what does that mean? Process 0 computed 1 into 2 and 2 into 4. So it basically added 8 and 2 and gave a partial sum of 10. Similarly, process 1, process 2 and process 3, each of them would have computed their individual partial dot products. Finally, we used the MPI reduction option to sum up all the partial sums by the root process, and this was computed and displayed on the screen. Thank you.